Yeah, it gives me pleasure to introduce Chantal Tax to give this talk on magnetic resonance imaging as part of our physics and medical physics offering, if you like. So, Chantal, over to you.
Yeah, thank you, Chris. So this lecture is about magnetic resonance imaging, or MRI. My name is Chantal Tax, and at the end of this lecture, you will hopefully have some insights into how MRI works and why physics is so important for medical imaging. So from the beginning of times, people have been fascinated by the question, how does the human body work? So of course, before we had any imaging techniques, there was no other option than cut the body open or to investigate certain body parts. So this is here depicted on a famous painting from Rembrandt on an anatomy class of Dr. Tulp. And the body in such an anatomy class had to be from an executed criminal, and it could only take place once a year. And in this case, the unlucky person was Aris Kind, who was executed earlier that day for theft. So MRI now allows us to look into the body without cutting. So if you've ever seen an MRI scanner, it's a pretty big machine with a long tunnel, which we also call the bore. And the table with the patient on it slides inside all the way towards the center. So MRI is absolutely fascinating technique, if you ask me. And I would like to tell you very briefly how I ended up developing such a passion for this physics underlying MRI. So I studied in the Netherlands, and already during my pre-university education, I very much believed that technology had the potential to really push healthcare forward. So as a bachelor program, I chose biomedical engineering to further explore this link between health and technology. But this program was actually quite broad, and it was ranging from biochemistry to tissue engineering, biomechanics. But I was mostly fascinated by biophysics, and in particular, imaging. So the underlying principles of MRI are of quantum mechanical nature, and you also need a good background in electromechanics. So if I would have to choose again, I would actually choose to study physics. And during my medical engineering masters, I actually decided to do just that. I followed courses from the physics bachelor that would help me develop my expertise in medical imaging better. Then in 2012, I started my PhD in medical imaging and MRI. And in 2016, I moved to Cardiff with where we have a very advanced MRI scanner where there are only 4 in the world. And here you can see 2 images of a brain. And only with scanners that we have here, we can get good signal in some scenarios, as you can see on the right. And yeah, no wonder that this scanner is sometimes called the Hubble Space Telescope of neuroscience. So MRI is very versatile. You can make many different images of the same organ by modulating the settings on an MRI scanner. And it's to date still a technique that is being researched very, very much, with thousands of scientists attending big MRI conferences each year. So what do we measure? So each pixel in an MRI image contains tissue on the millimeter scale. So these pixels are typically millimeters big. But if we zoom further, we would find cells that are about micrometers in size. And if we zoom even further, we would find molecules. And even further, we would find an atomic nuclei. which have a size of 10 to the power minus 15 meters. And some of these nuclei have a very special property, and we call this spin. So something happens if you put those in a magnetic field. So in 1924, a very famous scientist called Pauli actually postulated that some of these atomic nuclei possess this property that we call spin. So if we think of spin, we can actually think of a particle that is literally spinning around its own axis. But this is actually more a metaphor, because the spin that we talk about here is a sort of intrinsic property, but it's still very helpful to think of it as this classical picture of a particle with mass spinning around itself. So because this particle has mass, it leads to an associated angular momentum. And when does this happen? Well, this turns out to happen when the odd atomic, when the atomic mass number, so the number of neutrons plus protons, is odd, or when the number of protons is odd. So then we have this property called spin. And for us in particular, in MRI, the hydrogen nucleus is very important. So clinical imaging in patients is often called proton imaging for that reason, because it images the distribution of of hydrogen atoms in various molecules in our body. And the most important hydrogen molecules, atoms, are in water and in fat. So that's what we usually image. So on the one hand, we have this angular momentum because this particle is rotating and it has a mass. That's one important property. And on the other hand, this particle also has a charge, which is a second important property. And you can think of it as a tiny magnet, which is indicated in the right image. And in the left image, this is also indicated by this vector, this arrow, which we call mu. So it has a magnetic momentum. Now, because of these two properties, so the intrinsic angular momentum on the one hand, because we have a rotating mass, and the magnetic moment on the other hand, because we have a rotating charge, something special happens when we place such a particle in a magnetic field. And the theory of what happens to individual atoms is described by quantum mechanics. But actually, here we can use a classical picture to understand the behavior of these spins. So it turns out that these spins start to precess, so they start to sort of rotate around the main magnetic field that we applied. And this main magnetic field in this image is indicated by this arrow B0. So not only does this particle rotate around itself, when you place it in a magnetic field, it also starts to rotate around this B0 axis. So let's look at a short video, which is a classical analog of this precession given by Professor Paul Callaghan.
In thinking about magnetic resonance, we'll be thinking about atomic nuclei and their behaviour in a magnetic field. And I want to start by demonstrating some of the basic physics behind the behaviour of atomic nuclei in a magnetic field. And to help me do that, I've got a mechanical device, and it's this wheel over here. The first principle of understanding atomic nuclei in a magnetic field is to realise that those nuclei have magnetism. And so like little compass needles, when they're placed in a magnetic field, they tend to line up with the field. And I can demonstrate that idea with this wheel. There's no magnetic field that's playing a role here, but we have the Earth's gravitational field. And the effect of that gravitational field is that if I try to suspend this wheel on a string like this, it twists and finds a natural orientation pointing along the Earth's gravitational field. Why is that? Well, the combination of the weight force of the wheel and the string causes a torque to act. And that torque or twisting force reorients the wheel so that it hangs vertically. The second idea that's really important in understanding nuclear magnetism is the idea that the nuclei themselves have angular momentum. Let me demonstrate angular momentum with this wheel. I can do that simply by spinning it. Now let's try that same trick of suspending the wheel, like I did before, on the string, now that the wheel is spinning. Something really remarkable happens. That effect is called precession. And that precession idea is very, very important in understanding the way magnetic resonance works.
So these magnetic moments, they precess around the B0 field, and they do that with a specific frequency. And I've written an equation here. Omega is gamma times B0, and we already saw that B0 is the strength of the magnetic field that we apply, so the strength of the magnetic field in the MRI scanner. And the omega is the angular velocity in radians per second. So this describes how fast this rotation actually is. And it turns out that it has a very simple relationship to the strength of the magnetic field B0. And this equation is called the Larmor equation. And the frequency is called the Larmor frequency. And it's the most important equation in MRI. And this constant gamma is called the gyromagnetic ratio, and it's specific to a certain particle system. And it indicates the ratio of the magnetic moment to its angular momentum. And if you remember, those were the two important properties that MRI is based on. So a simple equation. So let's do a quick interactive question. If you go to this link on Mentimeter and you type in the code, you should be able to see this question. So the question is, what happens to the Larmor frequency omega if we have a stronger magnetic field? So remember again that this omega is gamma times B0. So what happens? The Larmor frequency increases, it stays the same, or it decreases. One vote for increases, decreases. So if we go back to the equation, then if the magnetic field strength becomes stronger, so if this increases and this gamma stays the same, because it's a property of a particle system, that means that also the Larmor frequency increases. So if you have a stronger magnetic field, and these magnetic fields are in the order of several Tesla, which is very, very strong, then your particles start processing faster. So it increases. But something else happens when we place these spins in the magnetic field. So in the absence of a magnetic field, the spins are pointing randomly. So if you would put all the spins in a certain pixel together, you would have a random distribution on a sphere of directions. But if you place them in the magnetic field, we already saw that they start to precess with the Larmor frequency. And in addition, there is a slight tendency of these spins to point a bit up rather than down. So to point a bit more along the direction of the magnetic field. So this leads to, if you take the sum of all these spins, this leads to a net magnetization in the direction of the magnetic field. So that's just this blue arrow here. It's the sum of all these individual spins. And these individual spins, they were all precessing, so they were all rotating also around B0. So this magnetization vector, which is the sum of all the individual spins, is rotating around itself, which is indicated with the red arrow here. So two things, the precession of the spin and some spins start to point more in the direction of the magnetic field, which gives us this net magnetization. So we looked a little bit at so the definition of nuclear magnetic resonance that we put on the slide from the beginning is that it was a resonance phenomenon of nuclear spins in a strong magnetic field. So we looked a bit at what are spins, what happens if you put them in a strong magnetic field. Now next, let's look a bit at what is this resonance phenomenon. So an important next step is that this distribution of spins, you can influence the distribution by adding energy to the spin system. And this can be done in the form of electromagnetic waves. So this means that we can manipulate these spins and the resulting direction and magnitude of this net magnetization vector in a controlled way. So we call this NMR resonance. And this manipulation only works if this electromagnetic wave has the same frequency as the Larmor frequency of the spins. And that's why we call it a resonance phenomenon. So we have seen that the spins precess with the Larmor frequency because they have both angular momentum and charge. And only if the electromagnetic wave has the same energy, only then the system can pick up that energy. And that's why we call it a resonance phenomenon. So luckily for us, the required frequency lies in the radio frequency range of the electromagnetic spectrum. So on the right, we have these waveforms with low wavelengths or low energy photons. So this is associated with radio waves, and that's where MRI operates, as opposed to, for example, X-ray imaging, which is based on much more higher energy waves. So because the energy of these waves is much lower, the interaction with tissue and the human body is very different, and MRI is therefore also sometimes called a non-invasive technique because there is no damaging radiation to the patient. Now let's see what happens if we emit such a radio frequency pulse. So on the left again, before such a pulse, the net magnetization is rotating around itself along the z-axis here, and it's rather difficult to observe. It cannot really produce any signal, a rotating vector that's just turning like this. So only if we introduce an RF pulse, a radio frequency pulse, that rotates the same frequency as a Larmor frequency, we can manipulate this magnetization, as you can see on the right. So what happens, it starts sort of spiraling towards the transverse plane, as we call this plane in X and Y here on the right image. So such a rotating wave or RF pulse can change the direction of the magnetization. And now this component becomes observable. So the detectors in an MRI scanner, which we call the receive coils, can observe this transversal rotating magnetization, and it induces a signal. So this can be measured with a coil. So let's look again at a brief demonstration, and in this video we can now think of the wheel as the net magnetization.
So what have we learned here? We've seen that in order to observe the precession, we need to have the axle tilted at some angle away from the vertical. And that begs the question, if we did start in that low energy position with the axle pointing vertically downwards, how could we disturb it in such a way that we could make the precession visible? And I want to demonstrate that to you. Just watch this trick. I did it. I used my finger to apply a torque to the wheel that brought the axle away from the vertical position into the horizontal. What was the basic idea behind the trick? The first thing is that I had to apply the torque in the horizontal plane. I had to apply it in a direction normal to, or at right angles to, the torque that the Earth's gravitational field is applying. The second thing is that I had to move my finger around in synchrony with the wheel, keeping the reorientation of that torque from my finger at the same frequency as the precession frequency. Let me just demonstrate that again. So this movement of the torque following exactly the precession frequency of the wheel is known as resonance. The frequency is exactly the same in both cases. And the idea of resonance is really central to what we'll be looking at when we reorient atomic nuclei from their natural equilibrium states in a magnetic field. So that's wheel mechanical resonance. When we perform nuclear magnetic resonance, we have to do the same trick. We have to apply a torque that's orthogonal to the torque of the magnetic field on the spins, and we have to have that torque varying with time or oscillating in exact frequency match with the natural precession frequency of the nuclear spins. And how do we apply that torque? We do it with another magnetic field. A magnetic field that's orthogonal to the main magnetic field that tries to orient the spins, and a magnetic field that's oscillating in time in exact synchrony with the precession frequency of the atomic nuclei.
So we can place a receive coil, which is essentially windings of copper wire, and this rotating magnetization vector will generate a time-varying magnetic flux. And according to Faraday's law, we get an induction and we get a voltage, and that is the signal that we can measure. And apparently, so that can be measured with a coil. And apparently, this vector also has a limited lifetime, this signal, because the amplitude decays over time. And this is because of a process that we call relaxation. So if we recap, we have put energy in this system using a radio frequency pulse. We have manipulated this magnetization vector away from its equilibrium state. But once we switch off this RF wave transmitter, then this process of relaxation occurs. And that means that everything will return to its equilibrium state. And this happens quite often in physics. For example, with temperature, if you heat something by putting energy, and if you leave it somewhere, then it will lose its energy again and cool down. So how exactly this relaxation occurs, for example, if it's fast or slow, depends on the properties of the tissue that you try to image. So for example, if the atoms can move freely or not, or if they cannot move freely, if they are attached to large molecules. And sometimes these properties also depend on the strength of the magnetic field. So by manipulating the spin distribution in different ways, we can learn more about tissue properties. And this is how we create contrast in MRI images, by mapping this measured property when you do a specific manipulation strategy of the spins in each pixel. So one last question in Mentimeter. Okay, is this true or false? The distribution of spins can only be influenced by an electromagnetic wave with the same frequency as the Larmor frequency of the spins. Yeah, this is indeed true, and that's why we call it nuclear magnetic resonance. So yeah, that was it. That was a short lecture. I hope you learned something, and thank you for your attention.
Thank you very much, Chantal, for that lecture. As you'll all have seen, there's a little bit of information on why MRI works and how MRI works. If you want to know a little bit about the kind of things that are done with MRI, there are other videos available on our YouTube channel that are there. There's one. Let me put a message in the chat. So this is a sort of complementary type video from one of Chantal's colleagues, Leo Beltracini, on what the kind of things we do with MRI. I'll post that in the chat shortly. Before I do that, any questions from anyone in general for Chantal at this stage before you sort of move into the separate off into the Easter School stuff? All right, well, while everyone's, there we go.